Sure. So let me.
Okay, it's a pleasure to introduce Dan Vu from the University of Texas at Dallas. And the title of the talk is Adaptive Bayesian Regression on Manifold.
All right. So I can start right now. So thank you very much for the introduction, and also thank you for the invitation. It is really my honor to have a chance to come over here and also share my research results. So, as you mentioned, the title of my talk today is Adaptive Bayesian Regression on Manifold. And this talk is based on the joint work with a group of people from Duke University, Tao Tang, Xiu Rencheng, and also David Johnson. So basically, my talk today is about like applying manifold learning technique in data science. So let me quickly uh, introduce some background of our problem. Uh, so we consider the following regression model as shown in formula one over here, where f star is an unknown regression function. And it is defined, right now it's defined for predictors, xi's in the d-dimensional Euclidean space. And here we assume that there's noise, which is just eta I, they are Gaussian noise with variance sigma squared. So what is the problem over here? So the problem is if we know that those samples are independently identically distributed in the Euclidean space, and the regression function is s times differentiable on the domain, then the min-max rate. So this is a well-known result. The min-max rate for the non-parametric estimation of the regression function is n to the power of negative s over 2s plus d. So the min-max rate, the understanding of min-max rate is basically the best, the smallest possible errors you can expect it in the estimation of the regression function. So here is up to some constant for this rate. And it's the min-max rate means that the estimation we do not specify the algorithm or any particular method in the estimation. So this is something like best you can expect. And let me explain the rate. We say that this rate over here is adaptive to both the smoothness level of the regression function and also the dimension of the domain. So what does it mean by adaptive? So basically, the results is that if the regression function itself is smoother, then we can expect that we have a better estimation of the function. So consider example, we know that if S1 is less than S2, then the class of CS2 function is a subset of class CS1 function on the domain. And then if you calculate the number, it shows that well, the error in the estimation for a function in the CS2 class should be smaller than the error in the error in estimation of a function in the CS1 class up to some constants. And another observation over here is if the dimension of the domain is very large, well, in this case, if you calculate this number, you see that this number becomes larger, and you expect that we're going to have a worse estimation. So the error will be larger. So in high dimensional data analysis, this is a very famous problem called curse of dimensionality, which means that the min-max rate can be extremely slow if the dimension of the domain is very large. So, is there any possible solution or for this problem? Well, yes. Uh, so basically, in practice, those high dimensional data, they usually have some low dimensional structure. And here we assume our low dimensional structure is a d-dimensional smooth closed submanifold in the Euclidean space. So basically, you consider those samples that are distributed on manifold in the Euclidean space. So in this talk, we focus on the Gaussian process regression. So the Gaussian process regression is a widely used flexible non-parametric method for regression, and it has ability to for answering quantification. So that's why it's commonly used. So let me briefly introduce the idea. So especially for those people who are not familiar with the Gaussian process regression. So in GP regression, you first construct a kernel function over here. It's called a covariance function. So the kernel over here we choose is just the standard square exponential kernel shown in the formula over here. Just be careful in the kernel, we apply the Euclidean distance between those two points, and epsilon over here is just the bandwidth of the kernel. And then we basically use this kernel, which it assign a prior, a GP prior. So it's GP prior is basically assumption on the relation between the value of the functions on the manifold. So we assign this hierarchical GP prior. So that means the value of the function, they satisfy a normal distribution with mean zero and with a covariance matrix, a covariance function given which is just a square exponential function. But it says it's hierarchical because we're going to assign a probability distribution for the bandwidth. So we assume that epsilon also satisfies the distribution, which is PT. So that's called the prior on the bandwidth. Now, if we consider our previous regression model, so given the training data, under this GP prior over here, there's like a posterior measure. So that's what you can infer by the Bayesian method is a measure in the space of functions, and we denote this measure as by pi. Well, if we know this, then we can express the posterior mean, which will be our estimator for this unknown regression function shown over here. So in fact, this formula is an abstract formula. So later on, I will describe the algorithm and I will give you an explicit formula by using the matrix induced by this kernel function. But this thing is very standard in Gaussian process, so I'll mention it later. All right. So what type of question are we going to study over here? So we're going to study a so-called convergence rate for the GP regression. Of course, in starting the convergence, you need to introduce some norm. So the semi-norm on functions, so function for example, L infinity functions. We consider two different norms based on two different designs. So the first design is called fixed design setup. So in the fixed design setup means that, okay, all those samples, they are given and they are fixed on your manifold. And the semi-norm we consider over here is just a small Ln norm. And the second design we consider is called the random design setup, which means that all the samples, all the predictors, they are either uh, sampled based on a density function on the manifold. So the semi-norm here we consider is the L2 norm of the manifold with respect to the density. So it's like a weighted L2 norm. Then we're going to also consider two type of convergence. So given the true regression function, so the first type of convergence is called the convergence rate of the estimator. So we say that it's Rn if the semi-norm between our estimator, so the estimator is shown in the previous formula by using that integral. So if the semi-norm between the estimator and the true regression function is less than Rn, and we consider the convergence in probability, so this probability goes in 1 as n goes infinity. So that's the first type of convergence. And the second type of convergence is so-called the posterior contraction rate. And we say that it's at least Rn if the posterior measure of the following event, so this event is defined by the semi-norm in the space of L infinity functions. So this event is the semi-norm between f and f star is greater than Rn. And this probability goes zero as n goes infinity. So again, it's a convergence in probability. Uh, so as a summary, quick summary over here, so we're going to consider two type of convergence of the estimator and also converge posterior contraction. And for each type of convergence, we're going to consider two setups, fixed design and random design. So that's the background. So let me say a few words about the previous result and why our results over here is meaningful. Okay, so here I focus on the Gaussian process regression with the square exponential kernels. So the classical result, which is by Van Watt and Van Zinten, they provide the contraction convergence rate, both the estimator and the posterior. Uh, it matched the non-parametric rate. So that's the formula over here. up to some log factor for regression function in the CS class in the Euclidean space. However, they also apply a hierarchical GP prior model. So that means they have to propose a prior on the bandwidth, and the bandwidth, the prior they consider is called inverse gamma prior. So I'll talk about this inverse gamma distribution later on. And also the second result is by Yang and Dawson. So they prove the convergence rate, which also match the non-parametric rate up to a log factor. So convergence here also means as a convergence of the estimator and also the posterior contraction. For those predictors on a d-dimensional manifold in the Euclidean space, and the regression function is defined on the whole Euclidean, ambient Euclidean space, which is CS class. And they also adopt hierarchical GP prior. So they, for the bandwidth, they propose the rescued gamma prior. However, I want to emphasize their relation, their result only works for S, the smooth level of the function, where S equal to 1 and 2. So let me combine those two results and give you a brief discussion. So first of all, both of those results, they propose a prior on the bandwidth, and for both the inverse gamma prior or what's called rescue gamma prior, those conditions, those requirements or those priors on the bandwidth, they require the knowledge of about the dimension of the domain. So in particular, you have to know the dimension of the manifold. In practice, sometimes it's really hard to estimate the dimension of your domain. So this is kind of like an issue over here. And also, I want to emphasize that for the second result is not adaptive to all level of smoothness. So what does that mean? So let's consider a simple example. Suppose our regression function is C3 function. Well, C3 is smoother than C2 function. So by our previous discussion, we know that we expect a faster rate, the corresponding C3 rate, right? So by substituting S equals 3 in this formula. However, if you apply Yang and Dawson's result, so that means you cannot directly achieve this corresponding C3 rate. So what you can really do is say that, oh, C3 is a subset of C2, so you apply S equal to 2 in this formula. So that's a problem because it shows that the rate does not achieve the ideal rate. So it's slower. So that's not the optimal result. Okay, so what is our goal over here? So our goal in this work, we have three goals. So first of all, we're going to propose an intrinsic level of smoothness for the regression function on the manifold, and also we're going to propose a prior on the bandwidth. So under the proposed prior on the bandwidth, we're going to show the adaptive convergence rate, which match the non-parametric rate up to a log factor. But here it's for all level of smoothness and any dimension of the manifold. And at last, we know that in practice, we're not going to estimate the dimension of the manifold. Instead, we're going to propose an empirical prior. So basically, we're going to propose a method, an algorithm, which will tell you how to choose the bandwidth based on the proposed prior on the bandwidth. So automatically, this choice of the bandwidth will satisfy our condition. So that's the three things we're going to talk about today. All right, so first of all, I want to just introduce a very elementary Riemannian geometry. So I want to discuss the holder class. So that's a level of smoothness for regression function on the manifold. So you just consider a smooth Riemannian metric with manifold with matrix G, and nabla here is that's a connection on the manifold. Gamma infinity, that's smooth sections in the tangent bundle, which just consists of those smooth vector fields on the manifold. For any f, which is a ck function on the manifold, so you calculate the L's covariance derivative of it, which is just a ck minus L tensor field of order L on the manifold. So that means if you just input L many smooth vector field, you get a ck minus L function on the manifold. And also you can calculate explicitly. So if you choose a frame, you can calculate the covariance derivative, the components of the covariance derivative by this inductive formula over here. All right, so that's pretty elementary. And next, we're going to consider a coordinate. So let psi be the injective radius of the manifold. And you just basically consider a ball of radius equal to the injective radius in the tangent space of the manifold at x. So the exponential map this uh, ball, tangent ball, to a geodesic ball on the manifold. So that's the normal coordinates. And we're going to compute the covariant derivative in the normal coordinates, which you just differentiate, you got a symmetric tensor of order k. So one thing I want to emphasize is we're going to introduce a norm on the case covariant derivative. So in geometric analysis, well, typically you just consider the Frobenius norm. While in contrast, we're going to use the operator norm uh, for this symmetric tensor. So here you just plug in the vectors, the unit vectors from the tangent space V1 to Vk, and you take the supremum, and then you take the supremum for all point x. So you got this operator norm. And if you apply the Banach theorem, it just says that, okay, you don't really, when you take the supremum for those tangent vectors, you can choose them to be the same vectors v. So you plug the same vector v in the tensor. All right, so to define the holder class, if you recall how we define the holder's norm in calculus, well, the idea is you have to compare the derivative at different points in our domain. So here we're going to compare the case covariant derivative on 2 points on the manifold. So you have to use the parallel transport. So we define the operator Pxy, which map from the tangent space of manifold at x to the tangent space of y. And we assume that y is within the injective radius of the manifold at x. Uh, so this Pxy is the parallel transport which move along the unique minimizing geodesic from x to y. So, well, basically, if you have a also normal basis in the tangent space of x, well, then by applying this parallel transport, it will certainly generate a also normal basis in the tangent space of y, moving those tangent vectors parallelly along the geodesic, and hence it will automatically generate a normal frame around x. So that's what we're going to use to compare the covariance derivative. So here is uh, our definition for the holders class on the manifold. So we introduce the k beta as holder coefficient for beta between 0 and 1. So it takes the case covariant derivative at first at x. Now you plug in a vector, a unit tangent vector, and you calculate the case covariant derivative function at y, and you move this vector v as a tangent space of x parallelly along the geodesic to becomes a unit tangent vector in the tangent space of y, and then you can take the difference and compare. And eventually, on the denominator, of course, you have to divide it by the distance to the power of beta. So the distance we consider here is just, of course, the geodesic distance. Now you can take the supremum over all y within the geodesic ball of radius equal to the injective radius at x. And you take the supremum eventually over all x. So that's the Holder's coefficient. And uh, so we have the definition. The k beta's Holder's norm of f is defined. Okay, it's a sum. The first k plus one term, they are just the norm on the case covariance derivative. First, the k covariance derivative, including the all zeros derivative, and plus its Holder coefficient. And we define in the holders class if this norm is less than infinity. So certainly this holder class defines an intrinsic level of smoothness on the manifold. Just a quick comment. So why we choose this norm, especially why we define the holder class like this, uh, it's just because this definition is easier for us to conduct analysis on this this Gaussian process setting. So that's a basic reason. Okay, so let me state our main results over here. So let's consider the regression function, which is in the k beta's holder class on a d-dimensional manifold in the Euclidean space, and we propose a prior PT on the bandwidth of the kernel epsilon square exponential kernel, and the level of smoothness is S, which is defined as the sum of beta and k. And now let's discuss the prior on the bandwidth. So how are we going to choose the bandwidth? What's the rule over here? So this density function PT should satisfy the following two conditions. So the first condition says that when t is small enough, you should have certain decay rate towards zero. So that means if t is between zero and a constant C1, which depends on the manifold, for example, the dimension of the manifold, it depends on the sample size, dimension of the ambient space, smooth level of the regression function, and so a key observation here is this C1 in fact goes to zero as n goes to infinity. So that means when t goes to zero, if you look at this function over here, when t goes to zero, it goes to zero. So that means your t should decay to zero as t goes to zero. So that's the first condition. The second condition is uh, is set at a certain lower bound on the decay rate. So that means when t is between some C2 and C3, again, they depend on the sample size, the dimension of the manifold, the dimension of ambient space, and also the regularity level of the regression function. Then PT should have a lower bound over here, given by this function. So where do those conditions come from? Well, in fact, it's kind of like a condition that mimic the gamma distribution on the real line. So this is kind of like a general condition. And also it worth to mention that our constant C1, C2 over here, it also depends on the dimension of the manifold and some geometric properties like curvature, those things of the manifold. So I did not specify over here, but yes, they do depend on your manifold. Okay, uh, so here's our main results. So first of all, in both the fixed design and the random design setup, if we concern the posterior contraction rate, then the posterior contraction rate to the true regression function uh, is at least well, it matches the non-parametric rate out to this log n factor to the power of d plus 1. And of course, there are some constants in front. I just omit the constant. And second of all, if we talk about the convergence rate of the estimator in both the fixed design and the random design setup, the rate also matches the non-parametric rate up to the log n factor. Okay, so that's a result. So finally, I want to talk about how to choose the bandwidth because we care about how practically we can use this method. So first of all, let me give you some background. So previously I mentioned the raised cubed gamma prior. So it just means that epsilon to the power of negative d over 2, where d is your dimension of the manifold, satisfy the gamma distribution. So automatically you can check that even in our proposed condition, this rescue gamma prior does satisfy the conditions. However, the problem is to construct such a prior, you have to know the dimension of the manifold D, and that's something we want to avoid. So we propose the following practical or empirical prior. Suppose we are given samples on the manifold. So we propose an empirical bandwidth prior that satisfies our previous condition by using the k nearest neighborhood kn method without an estimation of the dimension. So you just choose k be a quarter of log square n, where n is your sample size. And let Rkx be the kn radius. So what's kn radius? So that's the smallest radius such that Rkx, Euclidean ball, that's a radius of the Euclidean ball in the Euclidean space centered at x has at least k points. So that's a kn radius. We define Tn. So you have the kn radius for different samples xi. So we're going to calculate Tn, which is just defined to be the average of the kn radius. And Vn here is pretty simple. So you can regard this T as your bandwidth uh, of the kernel. So it basically is just a sum up all the values of the kernel. So you got this Vt. And we consider a prior Pt which satisfies this formula up to a constant. So eventually when we apply our method, we don't really care about the constant in front. So it won't affect the result. So we require that PT satisfies this relation for t between a quarter Tn, capital Tn square and 1, and it's defined to be 0 otherwise. So a few properties about this capital Tn and this Vn. So when n is large enough, the capital Tn square approximately proportional to n to the power of negative 2 over d up to some log factor. And we can show that uh, recall that in our previous slides, we have the conditions, we have those two constants, C2 and C3, which control the lower bound of the decay of the density. Well, here we can show that this C2 and C3 constant, in fact, lies between a quarter capital T n squared and 1. So the second property says that VNT also proportional to t to the power of d over 2 up to the log factor when t is greater than a quarter capital T n squared. So together with those two properties, you can justify that our prior, the density Pt, satisfy the previous two conditions. All right, so finally, just give me a second. I'm going to summarize our algorithm. So given the training data, xi's and yi's, and also the testing data, xi primes, we're going to predict the regression function over the testing samples. So what we're going to do over here is we're going to use a kernel function to construct a covariance matrix over the training data, and also we're going to construct a covariance matrix over the training and the testing data. So let y be a vector, realize the responses. So the marginal likelihood function can be defined by using this formula over here. All right. So for the given a prior on the epsilon, the bandwidth, the posterior distribution is proportional to the marginal likelihood together with product with the prior functions. All right, so here we have four steps for our algorithm. Step one, you just construct the marginal likelihood function and also the prior by our previous method. Now, based on the posterior distribution, you can just sample different k, let's say k different bandwidths. All right, so for each bandwidth epsilon, so you substitute the bandwidth into the kernel function, the posterior mean, which is the prediction. So previously, this is expressed by using that integral formula, if you remember it. But now we have an explicit formula by using this matrix inversion, matrix multiplication over here. So it gives you the posterior mean, which is our prediction corresponding to this particular choice, epsilon I. And the last step is if you want to predict the function, you just take the average of those predictions corresponding to different epsilon I, and that's your final result. All right, so a quick summary for my talk today is, so today I focus on the GP regression on manifold in the Euclidean space, and for functions with regularity defined intrinsically on the manifold, we still achieve the optimal rate, convergence rate up to log factor by using an extrinsic, for example, a square exponential kernel. But we have to be very, very careful over here. We have to choose the bandwidth that incorporates the manifold information. So it's kind of counterintuitive. I want to mention another result. The heat kernel on the manifold is the intrinsic kernel. And this can also be used for GP regression. And I do have a work which use a graph Laplacian technique that mimics the heat kernel and construct a GP regression method for regression function on the manifold. All right, so that's it for my talk today. So our results are available. So for this talk, it's applying N of stats. And for this graph-based technique on manifold, it's on GRSSB. So if you're interested in both results, you can look at them online. All right, so thank you very much for your time.
I will stop recording now.
Mhm.
Uh, Unfortunately, we don't have too much time for questions.
All right, no problem.